Hello, we are going to be learning how to multiply and divide radical expressions today. So here's in red our rule of thumb. The nth root of a times the nth root of b, as long as these indexes are the same, it makes multiplying really easy. It's not to say that you can't multiply if the indexes aren't the same, but it makes it easier when they are. So nth root of a times the nth root of b equals the nth root of a times b combined underneath the radical here. So I have some examples to kind of show you how that works. Here we have a square root and a square root. So we will get the square root of 2 times 8, which is 16. And of course, the square root of 16 is, voila, 4. Easy peasy Japanesey. Awesome. So and then in example B, we have 2 cube roots. And so we have negative 5 times 25, which I believe is negative 125. I could be wrong, but I don't think I am. 5 25s is 125, so that's negative 125. The cubed root of negative 125 is negative 5, because 5 times 5 times 5 is negative 125. So there we go. Not that complicated. I'm going to grab my calculator just in case. All right, so anyway, and then this last one, we've got square root of negative square root. And this one is going to be not possible. We don't even have to go any further. Because even if I multiply the two, I'm going to get square root of negative 16. And you can't take the square root of a negative number or the even root of a negative number. So that one's not possible. And that is how complicated this is. So at this point, we're going to have you do an example or 3 on your own. And no, this is what they're going to do. All right, so now we're going to go to the next one. And Gavin is really excited about doing this right now. So I'm going to do the first one, make sure that he remembers how to do it all. And then we're going to have him come up and do B. So this is another example of what you can do. This is a simplifying exercise. We're going to simplify these radicals. So we have to break this stuff down. We talked about this in the last lesson, that you have to make sure that the exponent and the index match. So right now, because there was no number written, we assume that it's a 2. In this case, the index is a 3. So our job is to factor this part into squares. So I'm going to go x squared times x, because x squared times x is x cubed. And then what are the 72? I need to find factors of 72 that have perfect squares in them. So 72 divided by 4 is 18. 72 divided by 9 is 8, but 8 still doesn't work. So 72 divided by 16, no. What's the next one? What should I be doing here? Why aren't you helping me? 36? Awesome, yeah. Okay, so it turns out that 72 is the same thing as 36 times 2. And again, I want to show you what I'm doing here. This is 6 squared times 2 times x squared times x. I have completely factored the radicand, and only numbers that have the exponent 2 will cancel with the index 2. So this 6 squared is going to come out as a 6. This x squared is going to come out as an x. But the 2 and the x will stay because they don't have an exponent of 2. So they don't get to come out of the house. So we talked about when you have a variable that has an odd exponent and an even index, you have to put absolute value bars. Okay? So the final answer for part A is 6 absolute value of x times the square root of 2x. So Gavin gave up on us now because he doesn't really think that he can do it anymore. Ha ha ha. But anyway, so now we're going to go to part B. And one thing that you want to double check is you don't have to put the bars if the directions say assume that all variables are positive. So make sure that you check that. I'm actually just checking it right now in my example, and it does say simplify and assume that all variables are positive. So because I can assume all variables are positive, I don't have to put the absolute value bar. So really, the answer is 6x root 2x. Awesome. Then we're going to come over here and do another example here. Again, same goal. We want to take the radicand, which is this piece, and rewrite it. So we're going to factor it into something that has an exponent of 3 because this index is a 3. So we're going to get n to the third times n squared, because that's going to give me 5, and one of them is a 3. Then I have to find the 80 and divide it by something that is a perfect cube. So 80 divided by 8 is 10, and we know that 8 is a perfect cube. 8 is 2 to the third power. 2 to the third power times 10 times n to the third times n squared. I cannot stress enough how much you need to be able to factor these things out into perfect cubes. Obviously not everything is going to work, but you want to make sure you can get the most out of your factoring. And again, just like the previous example, anything that has a third power will cancel with the index of 3. So this 2 to the third power will come out as a regular 2, and this n to the third power will come out as a regular n. And then the 10 and the n squared will stay because they don't have matching exponents. So this would be your final answer for that. So then you can do those on your own, and then we'll go on to one more example of multiplication. Something else that you can do here is multiply two radicals. All kinds of craziness going on here. So first thing I want to point out is you've got these coefficients in the front. Maybe we should try that in a different color, so that you're not like, what just happened? Awesome. Okay, this guy here is a 5, and this is a 2. I want to remind you that when you're multiplying lots of things together, it doesn't matter which order you multiply in. For example, if I had 2 times 3 times 5, I could go 2 times 5 is 10, and then 10 times 3 is 30. Or I could go 2 times 3 is 6, and 6 times 5 is 30. Or 3 times 5 is 15, and 15 times 2 is 30. They're all going to be 30. So you have 3 different things being multiplied. And in this case, you have 4 different things being multiplied. You have a 5 times this cube root thing, times a 2, times this cube root thing. So it makes sense to us to combine the two numbers that aren't in the cube root first. So 5 times 2 is just 10. And you can do that. You kind of just leave it over in the front. And then you can combine your two cube roots here. And we're going to get cube root of 54 times 5. So we can go ahead and do that. 54 times 5 is apparently 270. And then we've got x squared and x cubed, which is x to the 5th. And then we have y cubed, y to the 4th, which is y to the 7th jaw. And then we're basically going to continue like we just did earlier. I want to take 270 and divide it by things that have perfect cubes. The obvious choice is 27. 27 times 10 is 270. And we know that 27 is 3 to the third power. Or if we don't know, we should know. 3 times 3 is 9, 9 times 3 is 27. Then we're going to break up the x to the 5th and the y to the 7th. I hope that you're realizing that this is different from the last section in that we can't really go find things that multiply to get a 5. Because with a 3, 3 times 2 is 6, but not going to be 5. So instead of raising a power to a power, what we're doing is we're actually making them into two bases with this 2 powers of the same base. So this is going to be x to the 3rd times x squared. That's x to the 5th. And this is going to be y to the 3rd, or sorry, y squared to the 3rd times y. Okay? So what's happening here is 2 times 3 is 6. That's y to the 6th times y, which is y to the 7th. So there we go. And again, I have put everything that I can in cubes, and anything that has an exponent of 3 will cancel with the index of 3. So this 3 cube will cancel and it will become just 3. The 10 won't. This x cubed will cancel and become just x. This y squared to the 3rd power will cancel and just become y squared. And then everything else gets stuck in the little house. The 10 is stuck, the x squared is stuck, and the y is stuck because they don't have the same exponent as the index. And this would be your final answer. Oh, bad me, that's not the final answer. because we forgot there's a 10 over here. Remember this little guy? Shame on me. Someone should like fire me, just kidding. This 10 that was in front of the cubed root should have stayed there. We should have kept it there. And now we're going to bring it over here. And then 10 times 3 is 30, so our actual final answer will be 30x y squared cubed root of 10x squared y. That, indeed, is our final answer. So now I'm going to let you peeps try one on your own. Or, yeah, there you go. There's one that you can try on your own. Awesome. And then we're going to go to division. Division is done in much the same way. Here in the red, we have our little formula, if you will, our little property. If you have the same indexes that you're dividing, the nth root of a divided by the nth root of b, you can combine them into one fraction underneath the nth root. So that's convenient for us a lot of times because if you look at this example, the cubed root of 32 is some weird decimal. The cubed root of -4 is some weird decimal. But if I combine it into the cubed root of 32 divided by -4, that actually becomes 32 divided by -4 is, anybody? -8. -8, yes. And the cubed root of -8 is not a weird decimal. The cubed root of -8 is just -2 because -2 times -2 is +4, +4 times -2 is -8. So there you go. Really simple. So it's convenient sometimes for us to divide these problems. Okay, same thing's going to happen here. The cubed root of 162, I don't know. But if I combine this guy, I'm going to get the cubed root of 162x to the 5th over 3x squared. And 162 divided by 3 is 54. And if you remember how to do the properties of exponents, these x squareds cancel with 2 of the ones up here, leaving you with 3. So now this actually looks a lot cleaner than the original problem did. And 54 is not a perfect cube, but, sorry, here, it does have a 27 in it. 54 is the same thing as 27 times dose. Did you guys know that? And we already said before that 27 is 3 to the 3rd power. So we have 3 to the 3rd power times 2 times x cubed, and all of that is underneath this cubed root. And again, anything that has an exponent of 3 will cancel with the index of 3. So this 3 cubed will come out as a 3. The x cubed will come out as an x. And the only thing that stays inside is the 2 because it doesn't have a cube exponent on it. So put a little there. So there we go. 3x cubed root 2 is our answer for part B. Alrighty, so this is our answer there. So now you're going to try some. Aquí. Awesome. And then we're going to show you how to rationalize the denominator. It's not disgusting, it's beautiful. Alrighty, this is our last example for this lesson. So rationalize the denominator, what does it mean? When it asks you to rationalize the denominator, it means that you want to rewrite the problem, rewrite the expression with no radicals on the bottom, or in the denominator, which is the bottom. So all of these are bad. Square root on the bottom, square root on the bottom. And this, if you rewrite it, is cubed root 2 over cubed root 3x and radical on the bottom. So these are all bad news. So we need to figure out a way to fix them by rationalizing the denominator. So it's really easy to do. To rationalize the denominator, you need to multiply by the square root of whatever's in the bottom. But that isn't it. I got to show you how to work this, and I don't know how to tell you, so I'm just going to show you here. But basically, we said earlier that the radical only cancels when the exponent is the same. So on the top, you're going to get root 2 times root 3 is root 6. But on the bottom, you're going to get root 3 times root 3, which is root 3 squared. And since this doesn't have an explicit index, we assume that it's a 2, and they match, so they'll cancel, and then you'll have root 6 divided by 3, and now this is considered rationalized because there's no radical in the denominator. Okay? But again, the key here is that you want the exponent to match the index so they can cancel. So in this case, I am going to multiply by the square root of 5xy and the square root of 5xy for the same reason. I'm going to get on the top square root of 5x to the 4th y, because I'm going to have x cubed times x to the 4th. And then on the bottom I'm going to have 5 squared, because 5 times 5 is 5 squared, x squared, y squared. And since all of these have exponents of 2, they will all cancel. And on the bottom I will have 5xy. And on the top, we're not quite done because this x to the 4th can be broken down into squares. So that's going to be 5x squared squared y. And again, this, because it has an exponent of 2, will come out, and it'll just be x squared. It'll come out as an x squared, but the 5 and the y will stay in the square root. And then you have 5xy in the bottom from before. And this x will cancel with one of these. And your final answer is x root 5y over 5y. And no, you cannot cancel the square root of 5y with just 5y. So this is the answer for part B. I'll let you pause that if you need to, because I'm going to have to erase it because I kind of invaded my space for the other example that I was going to do. See, there's no space for C, so I'll have to go back and erase it. So hopefully you wrote that down, and I will erase you because you're not in my way. Awesome. And this last one here is my favorite, probably. A lot of times people think, oh, I got the hang of this. I've done 2 of them already, and I'm going to multiply by root 3x, root 3x. First of all, you have to have the same index. So this has to be a cubed root, that has to be a cubed root. And you're thinking, okay, it's going to cancel. But guess what? It's not. Because when you do that, you're going to get the cubed root of 2 times 3, which is 6x on top. And on the bottom, you're going to get the cubed root of 3 times 3, which is 3 squared, and x times x, which is x squared. And guess what? It's not going to cancel, because that is a 2 and that is a 3. Remember I said before that you have to make sure that the exponent matches the index so that it'll cancel. So in this case, we actually have to multiply by 2 of these. Okay? Or you could even put this 3 squared x squared, 3 squared x squared. Okay? The reason being that if I go 3 times 3 squared, now that'll be 3 cubed. And if I go x times x squared, it'll be x cubed. And then it'll work. Does that make sense? So I'm going to do that again. And hopefully you understand now why you have to multiply by 2 of them, not by 1 of them. So that means that if you had a 4th root, you would need 4 of these little guys. So here we go. I'm going to write this out over here now. We started off with 3 root 2 over the cubed root of 3x. So what I'm saying is we have to multiply by cubed root of 3x twice. There we go. I need 3 of them, because that way I'll have it cubed and it'll cancel with the 3. If this was a 4, you would need 4 of them. If it was a 5, you need 5 of them, and so on and so forth. So now that also affects the top, because now I'm going 2 times 3, which is 6, and 6 times 3, which is 18. And then I'm going to have x times x, which is x squared. So I actually have the cubed root of 18x squared on the top, we're gonna close this out here so that it's not in our way. And on the bottom, we're gonna have the cubed root of 3 to the third, because 3 times 3 times 3, x to the third, because x times x times x, and then they'll cancel, and we'll get the cubed root of 18x squared divided by 3x. Alrighty? And then you're done, because the 18 doesn't break down anymore for a cubed root. This would be our final answer. So now you can try this last example, and that'll be it for today. I need to come over here and turn this off.
Bye, everyone.
Bye.
I'm not really sure I know how to do that. Is it still recording?
I don't know.
Mark!